Okay. If you need, okay, please. You know that room was occupied by the faculty meeting. We have one, so today we still use this office. Classical physics can fail to explain this nature. Only can explain either low frequency or high frequency in their focal plan. Just remember, so energy is quantized. So by this, then we obtain this density. Here is this formula, square CQ h mu exponential h mu kt minus 1. Then we have two limits. In this low frequency, we have 8 pi mu square over q c to q and kt. It's a low mu, which is follow this Rayleigh-Jeans formula. And high, we have 8 pi mu q h bar cq exponential minus h kt, which is okay, so high, right? And correspond to this Wien's law. Wien's law, we have this a mu to the q exponential minus beta mu t. That time, I made a mistake. This beta is not temperature parameter, it is just parameter. Not this 1 over kt, so that parameter. So you can compare with this, so you know this parameter is h over k from this Planck's assumption. So this assumption, the key is we have this quantized, or quantized means the particle behavior, right? So that is the first example. Now let's consider the second example. Is the photoelectric effect, which another phenomenon which classical physics fail to explain this. That is a photoelectric effect. And to explain this one, Einstein was awarded by the Nobel Prize by this. So the phenomenon is we have a material which is metal. Okay. And the light come in. What we can see is we found the electron eject from the surface. So we have an electron here. This is the electrons eject or ejected from this metal. So this phenomenon gives us the relation between the kinetic energy with the kinetic energy. as a function of this instant light, we have a frequency mu. But the experiment observed is, it's very simple, just straight line. So that is experiment observation. Then try to explain this relation between the kinetic energy of electron and this friction of the light. If we use the wave behavior, it is not possible. So we figured that. Then the classical physics fails to explain this, right? Then the Einstein, okay. What Einstein Einstein, he adopts this Max Planck, Planck's the assumption, the quantized Einstein. He say, okay, the light, even though it's big, but it has the particle aspect, so that's quantized. If we use this one, and that became very easier to understand, because now we see this is a particle behavior. So in this particle, we give a name of photon, right? Photons, and each. Let me just let's use this. This single, right? Single. For each single photons, this suppose the energy is this one. Just remove n, right? So that the forgave increase. Then what happens is this interaction between the light, which is a photon, and electron. So if the interaction, then when this, if you consider particle, the interact or collide with the electron, so electron get, if there's an inelastic, get enough energy. If enough energy is enough over the work function, right? So this we check. So we say that the kinetic energy, if with this idea, that is very easily, that is the energy of the photon, subtract. Now we are going to say this is a work function, which is the minimum energy required for the electron to get rid of this the surface of the metal, right? So then the remaining part is this kinetic energy. Then you can see here, this is a kind of constant, right? So if this energy is large enough, then this work function, then we have the kinetic energy. So that is like a threshold, which have this. This corresponds to the energy of the light to be much larger than that, the W, the work function. Then the kinetic energy will have this, with increased larger energy, we have a larger kinetic energy, so they follow the straight line. That, again, to show this particle aspect of this light. But we know light is the wave. So that is two examples to show how we can find this interesting phenomenon which cannot be explained by the classical physics. Okay, now let's keep continue. How about the other, the wave aspect? If I use like this A, first A and B, another wave aspect of particle. How about the particle? So the particle also has a wave nature. That is from the other way, right? So either particle wave. In classical, they always exclude each other, separate. But let's see if we're down to the microscopic level, what we see is different. So now try to recall, right? So recall, actually, right? When we use actually, we are going to detect structure, crystal structure, right? So the crystal structure is like. This each one is an item or this a period. All right, so classical physics, we know when the light or instant light come to this, so we have given the lambda and this wave function, wave number, if this is X-ray, right? So that is light. Now we come to here also. Parallel the light. Then what we found is this reflect to here, and this one come to here and reflect again. Okay, so here we have the constructive constructive. If you detect here, you will see this very brightening, right? Circles or depend on symmetry when you have the detector here, right? So that's the detector here. What you can see, this is two waves, so some where they're constructive, some of where they're destructive. So what we found is this is called the Bragg diffraction. Bragg is diffraction. And this diffraction follows this, then ends this integer number, the incident light has a wave, right? So that is the lambda. That's always equal to, if this is d, right? And this is theta. So we know this is also theta. It is 2d sine theta. That is follow this law. Okay, so that is classical. Now let's consider electrons. Electrons are particles. How about electron? If we want to electron, try to incident to the crystal, what we found interesting phenomena. So okay, that with this electron we have initial momentum, right? P is mv initial. Then reflect here. Again, what we found, right? What we found here in this case, again, this constructive. We have this same thing. We call this diffraction. We call the matter wave diffraction. That means if the wave, yes, it is very easily to understand actually, so we know how the constructive of this destructive that due to this wave phase factor, whether they are same or 100% apart, right? So that is wave behavior. However, now we replace the actually by electrons. What we found at this detector, we also found this constructive and destructive, the pattern which is also follow this diffraction. So that is the wave nature, right? Okay, and when we found that this also depend give this, so it also followed. Now we are going to explain lambda. That here this is a momentum, right? Not lambda. But if we say it is also follow the same thing here. But now we are going to ask ourselves, what is the wave? So that means if we want to explain this phenomenon, we are going to use wave theory. If the electron behave like wave, we can successfully and easily to explain this phenomenon. So now this lambda, but we know that the electron is in momentum. It's not lambda. So we are going to find the relation between those. That means if electron behave like light wave, then we are going to see this new relation which we are going to explain. And this definitely cannot be explained by the classical physics. That is another phenomenon failure of the classical physics. Now, second example. So this is a first example. Now let's do another one. So we go to further. Second examples is Thomson's experiment. And you also know this, right? So now we have electron beams. Again, these are particles, right? So with the initial velocity here comes, so now we still have a particle, right? Now this is wave, right? So this is a wave. Yeah, this is a mu, right? So that is a frequency and that is the speed of velocity. Then comes through one of these very thin film. So here this is a target, which is very thin film. And what we found is, okay, it be scattered by kind of this, right, scattered. And then we have a screen here, screening. So that is screen, try to photographic, which is a photo graphic plate. So we found the ring, which is the diffraction, right? Again, that is a wave behavior. Diffraction rings, which is wave. So second one, we also found this interesting phenomenon, which cannot be explained by this classical physics. Okay, now if this is a wave, so again, so if a wave, so we have a lambda, and we are going to see what is lambda. What does mean is this particle has a wave function, a wave behavior, then if wave, then must be a wavelength. So we are going to find the relation between the wavelength and the momentum, that the particle behavior and the wave behavior. So that is the, by those C, we come to this conclusion. Light has a duality, right? We know light is wave, but now we can see, this is already even here. Yeah, we can see the light, the wave has the particle behavior. So that we know that is a duality. So we are going to say we have a duality, or the dual nature, let's see this. Before this, a dual nature of particles. We are going to discuss this. So particles, electron has dual nature because it's particle, but behave like wave. So that means they have either the aspect of wave aspect or particle aspect. Then we are going to discuss or find the relation between these two. That's the dual nature of the particle. How to describe this is proposed by this Flory hypothesis or relation, right? The Flory, which is relation. People usually use relation or hypothesis. So he tried to find the relation between the momentum and the wavelength, and this wavelength is not light. So there's a associated with particle we call the wave, matter wave, right? So he said, okay, based on the light has this duality, then the particle, any particle of the material also has this behavior. So let's start from light, the dual nature of radiation of light, right? And we know light is energy, so now let's think in the particle behavior, its energy speed. Okay. So particle aspect characterized by energy, right? And the energy of the photon, we know that we have considered like Einstein the relativistic effect. So I'm going to measure down this way. The red mass, and we know that for the photon, so here we discard this is the light, right? So that is a photon. Then that is 0, right? For the photon, remember? Okay, so that it is PC. That is the particle nature. Then, as okay, do this. So now PC. Okay. So now we find from here we have momentum of the photon is E over C, right? Okay. Now energy. Here, energy of light already quantized, right? So that is h mu. That is follow the Planck assumption. This is mu. Okay, C. Now, mu over C. No. Yes. lambda, right? So van der Waals lambda, so that is h over lambda. Now, you can see this is a wave nature, this is particle nature. Very interesting, he set up the relation. So now here, if the momentum has this one, and this is important, if you remember the Planck constant. He introduced this constant, he introduced this constant by defining this energy of the light. And this constant, you can see it is not arbitrary, not a constant number of parameter. It is very important, the parameter to characterize or set up a relation between the particle nature and wave nature. And of course, that is important parameter to go to the quantum mode, right? Or the microscopic level from the macro. Okay, so that is the dual. That is, we say, okay, so now this both say we have a dual element of light. And follow the same, we were going to say that is for the light, right? Okay, start from. And then for any particle, we are going to say at the macroscopic level. No, here, any particle, okay. It is a level. So for any particle, this we follow same. That is his assumption. His assumption relation that not start from the light, we can derive the relation between these two. For any particle, we always follow this. So that is the Broglie relation. Hypothesis or relation. That is for any. And this setup is the dual nature of the particle in the nature. A big particle and the wave. So they are always coexistent. Now, you may ask a question. For example, I didn't see the wave behavior of this, right? So how can we to believe or accept this concept? Let's discuss in the two limit, right? So, for the particle in the new domain, right? That means we are going to new in this in the magnet. Macro, let's see, in the microscopic domain or example like the proton. Sorry, let's consider proton forms zero mass, so that is not good, right? So let's consider proton. That is more than that, right? For example, proton, according to this, right? So the lambda is, I'm going to use index p. Lambda is h over p, right? We just have this relation, follow this de Broglie relation. Now let's see how much it is. Can we measurable? If measurable means yes, we can see the behavior, right? So now to do this, this is usually people use, and in the homework you can also do this way to multiply CC both sides and then multiply 2 pi. So h bar is h over 2 pi, right? So that is 2 pi h bar c, and then this one is h bar c, which we have numbers, and this 2 pi come down to here. Yeah, the inside this one is because this 2e and p, right, and c. I think 2 pi where it is. Should be have a 2 pi here. Then the mass, we know this one, right? So the mass, we know it's approximately, the numerator is about this number, mega electron volt, very high, right? And the term is femtosec, okay, the meter, femtometer, and then the denominator is about this number, which you substitute those, okay. Wait a minute. Oh, here. Okay, let me write down this one first, and then I give you. So that is about 3.4 10 to the minus 15 meter. So that is detectable. Table. Right, this is in this, the level. And here, this E is about 70. We use this estimate. So you can see here, this wavelength is 10 to the minus 15 meter. That is untransmitted 10 to the minus 10, right? So that's still measurable. Yes, okay, we can measure that wavelength, so that means we can see this behavior of the proton. But if for the particle in the macroscopic domain, let's see what the wavelength looks like. For example, let's consider a bullet. A bullet with the speed, and let's give usually in the classical we have a bullet. Okay, this mass is 0.1 kilogram, and the speed v is about 900 meter per second. So now let's look this lambda b. If we say that is has the wave behavior, so how much the wavelength? Let's look this at the macroscopic level. Then that's b h over p, right? P is mv. Now I'm going to use the mb is the bullet, and h. And h, we know that is I didn't give a constant, but you know the constant number, right? So let's just this is famous. You know this constant, so 6.626 multiply 10 to the minus 34 joule. Second, then this denominator, we have the mass, we have the velocity. So the result is about 7.4 10 to the minus 36 meter. And it's not easy. How can I say? It is not right. Difficult or cannot be. So far, at current the machine or the measurement or the instrument we cannot be detected. Cannot be easily detected. Which one?
Approximately, the velocity is 500?
900.
900.
So it's 9. So you see that is the big difference that this is almost the order of 20, smaller. So what's it look like? If you can still look like the wavelength behavior or the wave behavior of the proton, but this one, the wavelength is very small, so you can see the bullet size is big. But this the wavelength is compared with the size of bullet is almost equal, right? So that means it's a kind of particle. You cannot see this wave behavior is like particle behavior. But here, if the size is smaller, so if this is the size of the proton, but the wavelength actually proton is about same size actually, right? The proton is the size of the proton is about 10 to the minus 15, something like this. So that's we have to take into account this wave nature. But when the size is big enough, we will go to the macroscopic level. Yes, this wave behavior can be ignored since this wavelength is much small, and then it cannot see its behavior. So in particular, so now the conclusion is the particle behavior when we want to look the motion of the particle. So if you just focus originally on how the motion of or dynamics of the particle in the macroscopic level, you just consider as a particle. So Newton's, classical mechanics works. But if you want to see the property, physical property of particle, we have go to the quantum mechanics. You have considered this, like we solve the physics, right? Or we solve this system, then we do this, solve the Schrödinger equation and find the eigenvalues and find the excitation energy and which, whether it is semiconductor or conductor or metal. Those you have to go down to that quantum mechanics level, if you would consider the properties, right? The property of this particle. But if you just focus on this motion of this the particle in the macroscopic domain, okay, let's treat it as a particle. That makes sense? Okay. So that is the duality behavior, and then find the relation between this momentum and the wave. Now we want to go deep, understand this feature of this. So now this is one of the features we found in the quantum system or in the microscopic domain. So we are going to go to further to see is some other feature, right? So features of particles. If the particle size, so here so far we have found the duality, right? Now we want to need more. Is some more which is different from the classical physics, the particle described in the classical domain. So now, in order to find, because those are indirect observation, right? Not direct observer. We just see the phenomenon, and by this phenomenon we have say, if we want to explain this phenomenon, we have the assumption that is quantized. And then the quantized then follow the particle nature of the wave, and then by extent to see this the electron behavior of wave nature of electron. So we have this. Now how about others? So we are going to let's design, in order to that, design an experiment. This experiment we just design means in our mind we don't need to do it, but I think if you I'm not sure today this semester we have a quantum lab. Yeah, 601, 602, Dr. If not, yeah, I'm not sure. Usually we have, and then maybe if he designed one of the lab topic is this. So this is we call this the double slit exam. We call it double slit. Slits. Slit, right? So here, double means we have a solve. Let's consider classical mechanics first, or classical physics. Classical physics first. So we have a beam here, right? Source here. Then this beam we have this double slits. So we have S1, S2, and then we have a screen here, right? So screen is a detect screen. So what we found is if we close this one, just use one and get the color. Okay. So if we close S2, so then what we found, this only goes through the S1, right? So then the detector here, this intensity is I1. We can find this peak here. But if we close S1, then we have this they will go to here. So we have another one, I2. But if we open S1 and S2, we still found here we have two peaks. So the total intensity is simply this addition of these two. That is classical for, okay, that is for particles. Particles. If these are particles, and we know what happened, yes, yeah, we have this, right? That is I1, this is I2, this gives us I1 plus I2. If a particle, just particle behavior, simply addition this. But if this wave, classical wave, right? Again, we have the bin of wave here, and we have a double slit here, S1, S2. We have a screen here. Then if we close S1, close S2 here, then S1, so this is, will go to this, go through this, okay, then it's a wave, let's use this one, spherical wave, right? So we have a spherical wave, and the intensity here is again I1. So we have intensity I1. But if we close the S1, intensity is only I2. However, if we open both, what we found the intensity is not equal to simply addition. That is interference. So if we open the two, then we have found is like this. That is wave behavior, right? That is classically very easy to understand. And this one, so this is not simply add together because it's a wave. We have interference. Some of them constructed, some of destructive. So we got this interference. And here, interference I is I1 plus I2, and then you will have plus some phase factor 2. I1, I2, cosine delta, which is a phase difference between this, right? So that is very easy to explain. Now consider quantum particle, so or quantum view of the particle wave. Now this is a classical now. Quantum view of particles and wave. Okay, so now let's consider particle first. Suppose like electron beams, we have a source, so particle has the initial velocity and goes through this double slit, S1, S2. Then we have a screen here, again here. Again, so we have a closed S2, we have I1. So here they pass here. Okay, again we look here, I1. If we close S1, we get I2. So here we have I2. But, okay, I use color. But if open S1 and S2, what we found is intensity is not simply the addition to that means it does not follow this particle behavior. It forms like this wave as an interference. Okay, so now this is a new phenomenon. This is to prove again we have the duality. Now we want to have more feature, right? So we know, okay, in quantum mechanics view or quantum view, to view this particle, they always have a duality. So yes, we have. Now we have this. So first they come. Okay. Now we let's do this way. This is we consider when we open two. So we say, okay, this interference because the interaction between this the particle between this goes through two slits, right? But now if we do this way, we just try to one by one eject. So one by one, the first one only one, then either go to this one, or there we do not know. But just one, so they come to here. Then another time go to another one, maybe it's here or here, but then come to here. So that means only one particle, if go to here, how can the particle interact themselves to make this interference? Because from the classical mechanics, the wave, this one's due to the interference between these two, right? But here, if the quantum mechanics, if we just eject the particle one by one, we still see this. So what does it mean? That is, okay, the first, again, the duality, right? That means particle itself has the duality, has the wave behavior. Otherwise, you cannot explain this, right? So that is the first conclusion we can find. That is the users. First. Now we are going to do the second. To do the second, I'm going to, okay, let's plug again. Still particles, source here, we have 2, 3, S1, S2, and we have screen here. But what we are going to do is, we are going to add the light here. Okay, behind this this double slit. So what this light play the role? That means when we have suppose the electron, right? Electron charged particles. So when the electron goes through, the inactivated electron proton will generate a flash. That means if there's an electron go from here, come to here, then there's a flash. And we can see where this flash, we know, okay, the electrons go through either S1 or S2. We can detect. So that means this one, we can determine, let's say, determine the place, or the position, let's say. Determine the position of the electron, either S1 or S2. Okay, so now if we do this, what we found is interesting. The phenomenon, we open the two, right? So they still open two. Here, the intensity is reduced, becomes simply addition. Yeah. So now in this case, I is equal to the addition of 2. Not, or the interference disappeared. So that means the interference pattern disappeared. Disappear. What happened? So the goal is we try to find or try to determine the position or where it is. But when we try to use and how to find, we need the instrument or need the measurement, right? So this kind of the goal is the measurement. We want to measure the position. Then when we want to use the way, whatever the way or instrument that we want to determine where it is, then what happened as a result, we found the nature of the interference disappeared. So that means these states, they are not the same. That means they change the state of electron, right? So the second conclusion is measurement change the state of the particle or the particle. That is and why we do not know, we cannot prove by observation. This one is one of the postulate. Later we are going to discuss in quantum mechanics. We need a postulate, we need assumption, we need hypothesis, right? So that means it change and how to change. That is when we build up a theory, we are going to answer those questions. But here we found, by this design or in mind, design this experiment, we can find that there is something happen. And this is another feature of the quantum, the feature of this microscopic or quantum particle that if you really want to measure, you will check. The third one, this is a byproduct. What that means? Without this, if we remove this, it come back to here. But if come back, do you know when the particle will go to S1 or S2? We do not know. So if we do not know, it keeps the same. But if we want to know, it change. So what this means? Indeterminate, right? Okay. Indeterminate. So in quantum particle or quantum view to look this macroscopic particle, we cannot determine where it is. That means not like a classic particle, we can exactly know where it is. But here we do not know. If we really want to know, we use the try to measure, then what happens? The state change to another one. It is what you measure is not the initial states. Right? So that is these three features we found. Okay, now let this brief summary here. So now I come to here. One is duality. Second one, the measurement. Okay, the measurement. In or chain, right? Interfere with the states, right? Or status of particle. Third one is the particles are indeterminate, cannot be determined exactly. So with these three, at least we have some idea or picture about this. Now, we are going to analyze or discuss these three features one by one, how to interpret. We found those, we have a conclusion, we have this kind of feature. Now, next job is, okay, how to interpret. This is written in Word, but we are going to express in terms of this mathematically to find or describe those, right? So how to do that? First, right? First, now we are going to analyze. First, about the duality. How to describe the duality? What kind of wave? And what this wave means what, right? So that is first question we're going to answer. This one is famous Born's possibility assumption or interpretation. Born's probability interpretation. This year. Okay. What his interpretation of the duality, this is the first. This define the state of particle or system. Any of quantum system, right? We are going to, because it's duality, so we are going to is described by a wave function. Okay, here, wave function, I'm going to say here, the function, which is a function of R and T, right? So if a wave function exists in the whole space, that is wave behavior. Okay, so now characterize wave. Now, what is, let me first give, here, okay, I'm going to index here, energy and wave number. So here, that is, this is characterized, that is have a wave behavior, right? Wave nature. Now, the particle nature is characterized by those numbers. This, if these are discrete numbers, so that is a particle nature. Because here we have also the number k is, right? And the k and lambda has a relation, right? So that give a momentum particle nature. So the dualities come from first. We are going to characterize the wave nature, that is the wave function. That is not like the vector r, which is just a point to one in the space, one a particular point. No, this is defined in the whole space. Second, each wave function associates with given energy. So that the energy is characterized the particle nature of this quantum system, and also momentum. If we have the k, which is correspond to this lambda. So now we go further. The amplitude of this wave function is very important. Okay, so now this one. This one is amplitude. Okay, this one means what? It interpreted, because this amplitude is amplitude of this wave, right? Again, it's a function of r, the different position, different time. But this amplitude gives us the probability density. So we are going to explain this wave. Actually, it's not like a radiation. Not is a sound wave, not some other wave. It is a probability wave. I'm going to say. And first give this one. And this is a probability density. So what this means, if we have this multiply drq, so that the wave density multiplies the dr, now here, suppose this is r, right? And we have the q here. This is drq. That means in this solid, the element volume here, that gives us the probability, this product means the probability of finding particle at r plus r. Okay, between r and between r plus dr volume, element volume or volume element, right? So now they give an information. We do not know exactly where it is, but this magnitude or amplitude can give us predict a time t, okay, between the r and r plus dr, this volume element, to find this particle, how much the probability may be very less, may be very large. That information can give us. So that is this is the quantum states. It's an amplitude give us the probability to find the particle in where. So we call this is probability volume. That only gives us information about the probability to find the particle in some space, some position in the space. And since it's probability, so then we must have, if we integral in the whole space, the whole space. how much it is? V1, right? Whatever, that means to find the particle anywhere in space. If asked this question, what is the probability to find the particle anywhere in space? That's V1. It's been always in space, somewhere, right? And that we are going to use later, we call it normalization, right? The wave function, if not normalized, we have normalized, because that's only give us the probability information, not the others. So, now from here, we can have this to interpret or express this quantum states to represent its duality. That's the wave function, and this wave is a probability wave that only gives us the probability. Its magnitude or amplitude gives us probability to find particle in somewhere in space. So now if this, then we can also explain why the double slit has the interference. That is became simple. So now this, okay, let's, since we have S2, S1. I'm going to say the states when goes with I1 is say one state. It's two states. So when we come to here, right? Whatever have interference here. This is the total, right? Total is follow. Okay, let's be R anytime. Is follow this linear combination or superposition principle. But here is complex number. Right, because we know the wave follow this superposition principle. We can add this and then this. This is intensity, right? Intensity speed is amplitude of the total plus V alpha 1 psi 1 plus alpha 2 psi 2 squared. Then you can see there must be has this interference because you will see here, first one is alpha 1 psi 1 squared. And we have also the alpha 2 psi 2 squared, but we have also cross term, alpha 1 complex conjugate psi 1 alpha 2 psi 2 and plus alpha 1 psi 1 alpha 2 complex conjugate. And this part gives us interference, right? So the first one is I1 plus I2. If it corresponds to the experiment, we can say that is intensity. And then here, the second one, if you add those together, it is nothing but this interference. So I'm going to add this details, right? So now in that comes from here. That is because it's a wave, so this is not zero. If a particle, there's no this behavior. But if the wave, so you can see here, we can easily to explain this phenomenon that the interference in the double slit, if we consider the duality, use the wave function to represent. So that is how to represent this duality. Now, second one, we are going to discuss this one. I'm going to leave because this one we need one of hypothesis. Here, let's go to this one, indeterminate, right? So now let's see the first one, second one. Let's go to second one is indeterminate. But that means, or how to interpret it. We know this phenomenon, now we are going to interpret this one. And from this one, actors here already have the information here. Because this gives us the probability. So that means we cannot exactly know, we just only can predict sometimes, somewhere, the probability to find particle in this, but we cannot exactly say it's be here, right, 100% no. So that is this one. Okay, so probability, that is due to this. And with this probability, so we can introduce the uncertainty which Heisenberg first discussed. Use this idea so we can have this, to this correct in this determinate in terms of this Heisenberg's Heisenberg's uncertainty principle. Okay, this is from Born's probability interpretation, right? So now for the deterministic, the Heisenberg introduced the uncertainty principle. And those are later we are going to prove when we have established the quantum mechanics theory. So here, at the beginning, we follow those, but later you will very easily to prove this, right? So this uncertainty means that suppose we have this uncertainty, let's see, okay. So suppose we want to measure the particle in this position along the x-axis, and we do not know where it is, but we have the uncertainty that to measure this like the accuracy, right? How much accuracy we cannot give 100%, but we can say it's be in this range, delta x and delta px, momentum and position. Then suppose we have this, suppose, right? Suppose the uncertainty is delta x delta p, then they always have this relation. So delta x multiplied delta px always larger or equal to sum of this number. Now you can see the Planck constant come again. Very important, they characterize that these products always follow to be larger than this. So what that means, suppose delta x should be always larger than this h bar over 2px, 2 delta px. So if we want to measure x more accurate, that means we want to have this smaller, what happened? Right, so that means if the delta px larger, increase, right? The delta x decrease. Then, so when the delta x go to 0, that means we have lost the accuracy for the momentum. So what that means, we want to measure the particle. Where it is, what is momentum? However, we cannot make that accurate. If we really want to measure the position exactly, more accurate, then you cannot answer what is the corresponding the exact value of momentum. No way. That is the fluctuation is infinite. Or opposite, if we want to have this momentum, similarly, then the px always follow this. So the fluctuation or the uncertainty of this one always larger than this. So if we want to have a smaller, more accurate momentum, then your position is lost. Lost its accuracy, right? When the delta x increase, then you can have a decrease. So that means you cannot simultaneously get the exact moment, position and momentum. The uncertainty for momentum and the position always follow this. That is Heisenberg uncertainty principle. That means indeterminate. We cannot determine exactly, right? So we have to just only can give this probability or some uncertainty for the measurement to get this value rare case. This Heisenberg, the uncertainty principle also can extend. So we have extend it to any pair. But later we are going to, you may ask why this energy should be the time as a pair. Later you will see the like a conjugate either one or other. So the conjugate, if the x, the position conjugate momentum correspond to this pair, then the energy its pair is this time. So you will see here the energy, if you want to measure the system more accurate at which energy level, then it takes a long time because t speed, the fluctuation. So you cannot exactly say at that particular time energy is given. Of course, this is a case that we didn't say this eigenvalues, right? Eigenstate, that's another issue. So here that is also follow this. That means any pair also follow the Heisenberg uncertainty principle. Okay, now we are going to brief summarize. In this chapter 1, we just want to try to go back to the origin, ask our question. Before we establish quantum mechanics, we know we have some of difficulty, and we start from this difficulty. We are going to find something new and try to develop the theory, right? So now let me summarize, briefly summarize. Summary between the classical physics and the quantum, or classical mechanics and the quantum mechanics. Or in the quantum domain, we are going to see the difference. For example, here, the particle behavior, right? So we have the particle have a particle behavior. But here we have a duality. Okay. In classical, particle is particle, wave is wave, right? But in the quantum mechanics, particle and wave duality. We have considered this. So that is the difference between this concept. Second concept, in the classical, we can exactly term, right? The determinist means take, or certainty, we can certain, okay, we can exact determine their case. But here is indeterminate, deterministic, or uncertainty. That's totally different. The third one, the number or the physical value can change continuously. And here it is quantized. Quantized or quantization, right? The last one, this is the theory, or let's see, the laws or theory is based on the observation. We can direct observations, direct observe and summarize about the laws, and this laws is theory. But in quantum mechanics, there's no direct based on direct observation, and no direct observation. So we have base, then we have based on what? Based on the postulate or hypothesis to build up, right? To build up theory. Build up theory. That is also difficult or different compared with classical physics. Classical physics, let's just observe, try to summarize all the observation with 1,000 times and 100,000 times so we can summarize and find the role of underlying physics. But quantum mechanics, unfortunately, it is not have any direct observation, so we have based on the postulate. Now, that is before we establish quantum mechanics, we need first to introduce the postulate. So now how to establish quantum mechanics theory, we need or based on postulate. And then we are going to formulate, make a formulation, and then validate or justification. So here, this, because no direct observation, and here we build up theory, quantum mechanics theory, by formulas. Then we are going to validate. Okay. If yes, so that is new theory established. If no, nonsense, right? Then we have a give up or try to find another way to establish. So that is a framework of establishing quantum mechanics theory. Then we are going to follow this way. That is later in the chapter we are going to discuss here, chapter 3. This part. Okay. Now, the first we need, what is the condition for postulate, right? Then not only any arbitrary postulate, so we can have a lot of postulate or assumption, then we build our theory. If that's the case, then your theory is not transferable, right? So we need kind of conditions for postulate, not arbitrary postulate. We have asked ourselves such that with this postulate we can build up, but this be very solid, right? So the condition is first, okay. This should be based, even though we do not have a direct observation, but based on the indirect observation, lot of indirect, and those observation can sum up all this and get something key information. That is, so that's based on larger amount of or wide range of wide range of this range of experiment observation. Those are indirect, but based on this, so if the assumption or postulate does not just based on one particular, that is not the postulate, that is just some of a specific assumption, so that is not. We need to set up the postulate such that it be based on this. Second, if from this postulate we can extract from the postulate, if those postulates exist, we can extract the quantity, not just qualitative. Quality doesn't help us, right? We need quantity. So extract. Quantitatively information. About this system, right? About quantum system. So we need a quantum system, but those postulates can give us. That means from the postulate we can extract them. Otherwise, those postulates not meaningful, right? So we need them. and those they must be as small as possible. They cannot have 100 postulation, right? So it should be represent over this minimum size. They must be present the minimum set of assumption. Okay. Number 4, the last one. They need to be validated indirectly, right? So those assumptions or postulates later we are going to validate. If cannot be validated, cannot be justified by experiment, then those postulates also meaningless, right? So that means they need to be validated. All right. So this gave the condition for those. Now from next, we are going to see this, right? We are going to see which type of postulate can provide the base to establish quantum mechanics. So that is chapter 3. Now, from next Monday, next Monday, before we do this, we need to equip ourselves with enough math, because those postulates, for example, what is states? States are the one of these functions in the Hilbert space. So what is Hilbert space? The Hilbert space gives us the property of that, that means the wave function to follow that. And then what is this physical quantity? The physical quantity give us must correspond to operator. So what is operator? What is feature of operator? Hermitian and unitary operator. So those in chapter 2 we need first review this. I know most of you may have already idea, but I'm going to just first briefly summarize this. And with those ideas, when they discuss those postulates, that imply you already know that. They imply information, right? So that next time we are going to start from chapter 2. And then we go to chapter 3. Okay. Yes. You come in time.